When we start to look at solving trig equations, we need to be able to distinguish between what we call linear form and quadratic form. A linear form of an equation is an equation that contains our trig functions, but the powers of those trig functions are no higher than 1. Quadratic form means that we have at least one trig function either raised to the power of 2, or we may have two trigonometric functions that are being multiplied together. If the equation is in linear form and only one trig function is present, then we will use linear equation methods to get the function on one side and a number on the other side. Essentially, our whole goal for solving trig equations is to get the function on one side and a number on the other side. Sometimes, though, we have the quadratic form, and there are several different methods that we might have to employ in order to solve a trig equation in quadratic form. Very similar to the methods that we use in algebra to solve quadratic equations. We have what we call the square root method. So if we have only one trig function and it is being squared, and we have no linear term, then we can take the square root of both sides. And if you do that method, we want to make sure that we don't forget the plus and minus. If we have a trig function squared and there's another term that contains a trig function that is not squared, then we can try to rearrange the equation just like we would have done in algebra, get everything on one side, 0 on the other, and then try to factor. And then just like in algebra, once again, if you cannot factor something that's in quadratic form, then we have our quadratic formula. So if we were using the quadratic formula, we would get the trig function on one side equals, and then that old familiar quadratic formula on the other side. If there's more than one trig function present, say we have sine and cosine within the same equation, the first thing that I would recommend is that we get everything on one side, 0 on the other, and try to factor. If factoring doesn't work, to isolate the trig functions in each of their own linear equations, then we might have to start to use identities to rewrite the equation so that we can get it in terms of one single trig function. Sometimes we might have to square both sides of the equation, in which case we must make sure that we actually check our solutions in the original equation to see if it works. Once we have isolated the trig function to be on one side and we get a number on the other, our goal is to determine what angle would actually make the statement true. So when we solve, we're solving for angles. If we're asked to solve within an interval from 0 to 360 degrees, we're given that interval, we will be looking for angles in degrees on our unit circle. If we're asked to find angles from 0 to 2 pi, then we assume that we're working in radians. When we are looking for angles that satisfy the given statement, we make sure that we use reference angles to find all angles that have that trig ratio. So we're not looking in just one quadrant, we will be looking in two quadrants where the trig function is positive, since all trig functions are positive in two quadrants. And if we're given a negative value, then we're looking for both quadrants, the angles in both quadrants, where that trig function would be negative. So we're going to use our reference angles that we talked back in a previous section to determine all the angles within the unit circle that have that particular trig ratio. If we are asked to find all possible solutions, that means we're looking for all coterminal solutions to the angles that we find on the unit circle, then we are going to add 360 in, which means all multiples of 360, integer multiples, or integer multiples of 2 pi, depending upon if we're working in degrees or radians. Sometimes we will be able to write this more concisely by just adding 180 degrees times n, so multiples of 180 or multiples of pi. For tangent and cotangent, we will always be able to write it as multiples of 180. So when we are adding to find all possible coterminal solutions, tangent and cotangent will always be able to be written more concisely. In our first two examples, we will look at solving using linear equation methods. It is useful to think about the algebraic form of this equation before we solve the trig version of this equation. So when you see a trig function, let's think about that for a minute in terms of the algebra. So think about tangent theta as being just a variable like x. So 3x minus square root of 3 equals 0. The methods that you would use to solve this equation in algebra will be the same methods that we will use to get tangent theta by itself on one side of the equal sign. So the first thing that we're going to do is we're going to add square root of 3 to both sides. So we get 3 tangent theta is equal to positive square root of 3, and then over here we would divide then by 3, and that's what we're going to do here. We're going to divide by 3. So we get tangent theta is equal to the square root of 3 over 3. Now this would be our first goal, to get the trig function by itself on one side and the number on the other. So the next thing we want to know is what angle would give this trig function value. So we're looking for the quadrants where tangent would be positive. So we want to look in quadrants 1 and quadrants 3. So what reference angle family are we looking for? So remember that before we rationalized, if I was to unrationalize this, I would end up with 1 divided by the square root of 3. And remember that tangent is the y value divided by the x value. So I'm looking for points on my unit circle that if I did y divided by x, I would get 1 divided by the square root of 3. Well, the points that I have are all divided by 2, so let's write it in the actual form of those x and y values. So that would look like 1/2 divided by the square root of 3. So we're looking for points that have a y value of 1/2 and an x value of the square root of 3. So it looks like we're dealing with the 30-degree angle family. So that's our 30-degree angle here, and keep in mind that we're talking about that reference angle family. So when we go into quadrant 1, we have a reference angle of 30 degrees. Remember that reference angles start at the x-axis and then go up into the quadrant from the x-axis. So we have a 30-degree reference angle there, and then we're going to use that reference angle family, and we're going to go 30 degrees also into quadrant 3. So we're looking at 210 degrees and 30 degrees. So the angle that has a tangent value of positive square root of 3 over 3, there are two angles that have that positive tangent value, and that would be 30 degrees in quadrant 1 and 210 degrees in quadrant 3. So we always want to make sure that we look in both quadrants where that trig function is positive. Now, these are our two solutions over the interval 0 to 360 degrees. What if we were looking for all possible solutions? So not just the ones on the unit circle, but maybe I want to go around the circle twice, or 3 times, or 4 times. Well, we also want to give all possible solutions in terms of all coterminal solutions. So if I went around the circle again, let's say that I went all the way around again, and I hit and landed on this spot again. So I'll go around all the way around again. This angle, 30 degrees, is coterminal also to 390 degrees, for example. So there are several angles, all possible coterminal angles, that all have exactly that same positive tangent value. So when we're looking for all possible solutions, there's a couple of different ways that we can write this. Looking for all possible solutions, one way to do it is to take each angle and add multiples of 360. So we could say that to find all possible solutions, you could take 30 degrees and add 360 times integer multiples of n. So 1, 2, 3, 4, negative 1, negative 2, negative 3. So n is just any integer. So any integer multiples of 360 added or subtracted to 30 degrees would find all possible coterminal solutions to that angle 30 degrees. And we could also do the same thing for 210 degrees. So we take that angle and add all possible multiples, integer multiples of 360. So that would give all possible solutions that have that positive tangent value. Now, there is a more efficient way of writing this. If I look at these 2 points on my circle, so we look at the 2 points here on the unit circle, we notice that 30 degrees and 210 degrees are actually equally spaced around the circle. They are 180 degrees apart. So if I started at 30 degrees and I went 180 degrees in the positive direction, and then I did it again from 210 back to here, another 180 degrees, I could go from point to point to point. I could keep adding 180, and I keep finding all these coterminal solutions a little bit more efficiently just by adding 180 degrees over and over and over again. So another way that we can write these solutions, which this might be the solution that you would see in your book, is to take the smallest angle that we found on the unit circle, which would be 30 degrees, and add multiples of 180 to that angle, and then we would actually land on 210 and then back to 390. We would actually keep finding all those coterminal solutions in a little bit more efficient way. So here in our next example, we're going to solve once again using linear methods. So if you imagine sine x, if you think about that as being like, well, let's come over here. If I thought about that as being like a linear equation in algebra, that would look like, let's call 2 sine xy, so like 2y plus 3 equals 4. And remember, the first goal would be to get that trig function by itself, in other words, getting y by itself. So how would we accomplish that? Well, I would subtract 3 from both sides of the equation. So we would have 2 sine x equals 1, and then divide by the number that's multiplied times the front of that trig function. So sine x is equal to a positive 1/2. So we're looking for our angles on the unit circle from 0 to 2 pi, which means we're working in radians. So we're going to report our answers in radians. So sine is positive, and sine is positive in which 2 quadrants? So we're going to find some angle from quadrant 1 and also from quadrant 2. So sine is positive in both quadrants. What reference angle family are we talking about? We're looking for sine is 1/2. Well, that would be our 30-degree reference angle family. So 30 degrees into quadrant 1, and then 30 degrees into quadrant 2. Or pi over 6, our pi over 6 family, so pi over 6 into quadrant 1, and a reference angle of pi over 6 into quadrant 2. So the angles that we find in quadrant 1 would be pi over 6, and in quadrant 2, 5 pi over 6. Now if we're looking for all possible solutions, I'm going to take each of the angles that I found on the unit circle and we're going to add multiples of 2 pi. Since we're talking about radians, a complete rotation all the way around the circle would be 2 pi. So we could say 2 pi times n. So integer multiples of 2 pi. And we'll take the second angle and do the same thing. Now these two angles are not equally spaced around the unit circle, so there's not a more concise or nice way to get from angle to angle. So this would be the most efficient way to describe all possible coterminal solutions for the two angles that we found. Now we're going to start to look at equations that come in quadratic form, which means that one of our trig functions will be squared. And we're first going to talk about the square root method. So if we think about this in terms of how we would have thought about it in algebra, let's look at the cosine function as being like y, and since it's squared, we'll think about it as y squared. And this would be a quadratic equation without a linear term. So we have the quadratic term, so we have the function, we have the term where the variable is squared, and then we have the constant where we're missing the what we call the linear term. In this case, we would get the number, all the numbers on one side, and we would get y squared by itself and take the square root of both sides. So that's what we're going to do here. We're going to add 1 to both sides, and then divide by 4. So we want to get the numbers on one side, and then we want to isolate that trig function squared on one side. As soon as we isolate that trig function squared, then we want to take the square root of both sides of the equation. So now we're left with cosine x. So that's my goal, is just to get the trig function to the first power by itself. And when we take the square root of both sides, we want to make sure we put in the plus and minus. Square root of the top is 1, square root of the bottom would be 2. So we're looking for all solutions of this equation. So all possible solutions, we're not given a specific interval, and we're going to give the answers here in radians. So which quadrants are we going to be looking at? Well, we're looking for quadrants that have a positive cosine value, which would be quadrant 1 and quadrant 4, and also a negative cosine value, which would be quadrants 2 and 3. So we're looking for all angles that have this cosine value of positive 1/2 and negative 1/2. And remember, on our unit circle, that would be the pi over 3 family, where x, that x value is 1/2. So that's our pi over 3 reference angle family. So this is our pi over 3 reference angle, and we have pi over 3 going into each quadrant. So remember, reference angles have exactly the same cosine value, plus or minus, depending upon what quadrant that we're in. So we want to find all of that pi over 3 family. So that would be x is equal to pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Now we're looking for all possible solutions, not just the ones on the unit circle, which in that interval. So in order to find all possible coterminal solutions, we could add 2 pi n to each of these. But that might not be the most efficient way to do it. Now the angles are not equally spaced, starting at 60 degrees. If I go to 120, those are 60 degrees apart. But then from 120 to 240, those are 120 degrees apart. So there's not a quick way to get from the first angle to all 4 of the rest. But there is a fast way to get from 60 to 240, and then back to that point, a coterminal angle at 60. These are exactly halfway around the circle from each other. They're exactly 180 degrees apart. And we're talking about radians, so to get from 60 to 240, or to get from pi over 3 to 4 pi over 3, all I have to do is add pi. So we are going to represent all possible solutions in a more concise way by saying pi over 3 plus, and then it will add multiples of pi. So to get from pi over 3 to 4 pi over 3, I can do that very efficiently just by adding multiples of pi. Now how do I get from 120 to 300? Well, we would add 180 degrees. So I can say 2 pi over 3, so the smallest of those two, and then we'll add just multiples of pi. So the most efficient way to represent all possible coterminal solutions to the 4 that we found on the unit circle would be to start with the smaller of the 2 that are halfway around the circle from each other, and then add multiples of pi. Start with the smaller of these 2 that are halfway around the circle from each other and add multiples of pi. Alright, if we think about this equation in algebraic terms, we could think about tangent as being like, let's say, y squared. So we would have something like y squared plus 3 equals 0. And if I was solving for y, once again we have a quadratic term and a constant term, but we do not have a linear term, so we can actually use the square root method in order to solve. So we want to subtract 3, we want to get tangent squared by itself on one side. And then we'll take the square root of both sides, and that leaves us with tangent x, so tangent to the first power of x, equals, well, plus and minus the square root of negative 3. Well, if we think back to our algebra days, the square root of a negative number would be an imaginary number. So we could think of it as the square root of minus 1 times the square root of 3, and the square root of minus 1 we know is I. Well, this would mean that we would have to have a tangent value of some angle give us an imaginary value. We have no imaginary tangent value, so this particular equation has no solution. For the next 3 examples, we're going to look at using factoring to solve trigonometric equations. Once again, when we look at these equations, we want to think about them in the algebraic form. So if we see sine squared and sine, let's think about that as being like a variable from algebra. So let's think about minus 2y squared. Since we have sine squared, we'll think about it as variable y squared equals 3y plus 1. So in algebra, if you were going to solve that equation for y, the first thing that you would try is to get everything on one side and try to factor. And it doesn't matter what side we bring everything to. So I'm going to go ahead and bring everything to the right hand side and get 0 on the left hand side. Alright, now we're going to try to factor what we have. So this is similar to 2y squared plus 3y plus 1. So if we were factoring that, we would split it up as 2 parentheses, and we need 2 sine x and sine x. The signs are both plus, so we'll put plus and plus, and then 1 and 1. And we could always check that by foiling it back out. Now that it's factored, now we're going to do what we would have done over here once we factor. We're going to set each of these factors equal to 0. Once we do that, now you notice that we have an equation, 2 separate equations, where sine x is raised only to the power of 1. So now we have 2 linear equations, or equations in linear form, and we can actually solve by getting sine x by itself in each of these linear form equations. So we'll add 1 to both sides, and then divide by 2. So now we have sine x is equal to 1/2, and then in this equation we're going to subtract 1 from both sides, and we get sine x is equal to minus 1. And we're asked to solve this equation over the interval from 0 to 2 pi, so we are working in radians. And we want to know, when we look on the unit circle here, what angles have a sine value of positive 1/2. And we're looking for a positive sine value, so we want to make sure we look in both quadrants. quadrants 1 and quadrants 2 where sine is positive. And we're looking for a sine value of positive 1/2. And that's our 30-degree angle family, reference angle family, or the pi over 6 reference angle family. So that would be here and here in quadrants 1 and quadrants 2. So the reference angle is pi over 6. So we get pi over 6 and 5 pi over 6. Both of those angles have a sine value of positive 1/2. And for this equation, we're asked to find what angle has a sine value of -1. And of course, that would be down here. And that answer for that part would be 3 pi over 2. So we have 3 solutions. We want to solve the equation tangent squared x plus tangent x minus 2 equals 0. And we're looking to solve it over the interval from 0 to 2 pi, which means that we're working in radians. And we're also asked to solve for all possible solutions. So let's start by thinking about tangent x as being like a variable in college algebra. So this would be the same thing as like u squared plus u minus 2 equals 0. The first thing that I would try if I was solving that in algebra would be to factor. So let's try the same thing here. Set up our 2 parentheses. It's already set equal to 0, so all we have to do is factor this trinomial. We can think of it as tangent x, so u times u, or tangent x times tangent x. And the numbers that we have to choose from at the back would be -1 and 2, or 2 and -1. So we have opposite signs, and let's say -1 and positive 2, and if we FOIL that back together, we should get that original 3 terms. So now that it's factored, we're going to set each of those factors equal to 0. And then solve the linear forms of each of these equations. So plus 1, we get tangent x is equal to 1. Minus 2, we get tangent x is equal to -2. Now, working with our unit circle, we're looking for tangent x is equal to 1. Tangent x is equal to 1. We're looking in quadrants now 1 and quadrant 3, and we're looking for the places where x and y are exactly the same. So remember that tangent x is sine divided by cosine, or y divided by x. And if I take the y value and I divide it by the x value, if those x and y values are the same, then we get positive 1. So we are describing our 45-degree reference angle family. So 45 degrees, or pi over 4 radians, into quadrant 1. So our first solution for that angle we'll call pi over 4. And then in quadrant 3, that's the 5 pi over 4, that's our pi over 4 reference angle family going into quadrant 3. So this negative divided by negative will give us that positive 1 that we want for tangent. So we get 5 pi over 4. So let's list out those 2 solutions. So we have pi over 4, 5 pi over 4. And we actually have one more equation to solve, and this is a tangent value that we're unfamiliar with. We know that we're going to be looking in quadrant 2 and quadrant 4, because that's where tangent is negative. So we're looking for angles in quadrant 2 and in quadrant 4. So keep in mind that we always look in 2 quadrants, both quadrants, not only where tangent is positive and with those familiar reference angles, but also where tangent is negative in both quadrants and then even angles that are maybe unfamiliar. So let's look at tangent x equals -2. Well, we don't know that, so we're going to put that into our calculator using our inverse tangent function. We're going to feed it the tangent value and let the calculator tell us the angle. So the angle that we get when we put this into our calculator, make sure your calculator is in radian mode. We're working in radians. And the value that we get is going to be a little strange looking, but that's okay. It's in radians, and it should come out to be a negative value. If you remember our discussion for the inverse tangent functions, tangent inverse will spit out an angle from quadrant 4, and it's going to think of those angles as being negative angles. So what we get is expected. We get -1.107148718. So there's the entire angle that we get in radians, and that's an approximation from your calculator. Well, we don't want this because this is not within our interval. Remember, the interval that we were looking for down here was from 0 to 2 pi. Well, this is a negative value, and the negative value would be less than 0, and that does not fit in our interval. So let's think about where this would be on our unit circle. So I'm going to come up here. I'm going to draw a little separate circle up here. Okay. This is definitely in quadrant 4. We're going to start here and think about a negative angle in, let's say it's about right there. So this would be -1.107, etc. for that angle. And this is not the angle that we want. We want an angle that's coterminal to this, that lives in the desired interval from 0 to 2 pi. So let's add 2 pi to this. Now if we add 2 pi to this, we actually get an angle that lives within the interval that is coterminal to this. So we're describing the same angle, except instead of thinking of it as a negative angle, we're going to go from here all the way around to here, and we're going to consider that to be a positive angle. So when I add 2 pi in my calculator, I get 5.176036589. Okay, so there's that angle. There's one of our solutions. Now, we have another solution. Remember that tangent has a value of -2 in quadrant 4, but also in quadrant 2. Now, how do we determine what that angle is? Well, the reference angle that we used, the amount that we went from the x-axis into quadrant 4, this will be called our reference angle. And we want to go the same amount from the x-axis into the other quadrant where tangent is negative, also into quadrant 2. So we're going to go up that same exact amount and determine what angle this is in quadrant 2. So we're going to use that same reference angle of -1.107, and we're going to go that amount from the x-axis into quadrant 2. And we want to figure out what that angle is. I'm going to do this one in green. Okay, so we want to know what this angle is here. So it has the same reference angle as that angle. But we're going to know if I start here and I go in the positive direction and I stop at that point right there, what angle has a reference angle? What angle in quadrant 2 has a reference angle of -1.1? Well, in order to find this angle, let's think about what we're working with here. If I did a half rotation, that would be a radian value of pi, but we don't want to do a half rotation. We want to stop just this amount short of a half rotation. So we're going to subtract from pi. So we're going to say pi minus that reference angle 1.107 148718. So when you put that in your calculator, subtracting off that reference angle from pi, then we actually get this angle in green that we want, that quadrant 2 angle, that also has a tangent value of -2. So that angle would be 2.034443936. So we get two more solutions for this equation. They look kind of weird, but that's okay. So we're going to write those two down as two more of our solutions. We have 5.176036589, and then the quadrant 2 angle. Okay, so these are our four solutions that we found that fit in the interval from 0 to 2 pi. Now if I want all possible solutions, there's we talked about the long way of doing it and the short way of doing it. The one way that I could do this is to add 2 pi in to all four of these angles. Well, there's a shorter way to do that for this one. If we notice that the angles pi over 4 and 5 pi over 4, these are actually directly across the circle from each other. They're 180 degrees apart, or pi units apart. So we're going to take the smaller of those two angles, and we're going to add multiples of pi. And this would be the more efficient way of writing them, instead of just adding 2 pi, 2 pi, 2 pi in to all of those. And then this will always happen for tangent. If you notice, these two angles are actually 3.14. If you were to put these in your calculator and subtract them, your answer would be approximately pi. So if you take this smaller of these two angles, so we'll take the smaller radian value, if you were to add pi to that, then you would actually get the quadrant 4 angle, 5.1, etc. So what we're going to do is we're going to just add multiples of pi into this one as well. So this would be the more concise way of doing it. Keep in mind that you could also take all four angles and add 2 pi into all four, and you would also have all possible solutions. Anytime that we can write it more efficiently than we want to. When you're working with tangent and cotangent and tangent have periods of pi, which means that they repeat themselves every pi units. So we will always be able to write tangent in the more efficient way by just adding pi in to the smaller of those two angles. In this example, we see that we have two trig functions. We have secant and tangent within the same equation. The first thing that I want you to do is I want you to think about this in terms of the algebra. So each of these trig functions, we're going to think about them as a different variable. So we have secant squared. Let's think about secant as being like x. So we'll say x squared. And let's think about tangent as being y. So we have something similar to this if we were solving equations in algebra. The first thing that we want to try, especially if we have two different trig functions, is to attempt to bring everything over to one side and factor. So let's try that first. And if that doesn't work, then we can try something else. But let's first try to bring everything over to one side and factor. So let's subtract 2 times tangent theta from both sides of the equation. So minus 2 times tangent theta equals 0. Now, if I was doing this in algebra, if I were to subtract and set it equal to 0, what do you notice is common between those two terms? Well, they have a common factor of y that we could factor out. Here we have the same thing. We have a common factor of tangent theta. So let's bring that tangent theta out to the front, and what we're left with on the inside now is secant squared theta minus 2 is equal to 0. Once we have factored as much as we can, we have two things multiplied together that gives us 0. We can set each one of these individually, each one of these factors individually equal to 0. Now what we see is that we actually have now two separate equations. Now each one of these equations only has one trig function, which is what we want. So now we have tangent theta equals 0. That's basically already solved how we want it to be solved. All we need to do now is to determine what angles describe this. Tangent of some angle equals 0. Well, remember that tangent is y over x. In order for that fraction to be 0, what would have to be 0? Well, in order for y over x to turn out to be 0, it doesn't really matter what the x value is. We're looking at something that has a y value of 0. So points on our unit circle that have a y value of 0. That would be right here at 0 degrees and 180 degrees. So we're working in degrees, just to remind us there. So 0 degrees and 180 degrees would be places where we have tangent values of 0. Okay, so we got that one done. We have two angles now for our solutions. Here we need to solve by using the square root method. We have the quadratic term, we have the constant term. We do not have a linear term. So I can solve using the square root method by adding 2 to both sides. And once I have that secant squared equation by itself, we can take the square root of both sides. And remember that when you take the square root of both sides, you have to put in the plus or minus. So we have secant theta is equal to plus or minus the square root of 2. Now, sometimes it's hard for us to remember what angle has that secant value of plus or minus the square root of 2. So we can always think about it in terms of the reciprocal function. So the same angle that has a secant value of plus or minus square root of 2 has a cosine value of that same angle as the reciprocal of that. So that same angle also has a cosine value of plus or minus 1 over the square root of 2, which if we rationalize that, it looks really familiar, square root of 2 over 2. And we can see very easily quickly that that's our 45-degree reference angle family. So 45 degrees into quadrant 1, 45 degrees into quadrant 2, 45 degrees into quadrant 3, and 45 degrees into quadrant 4. And we're looking at all 4 quadrants this time because we had that plus or minus. So we're looking at 315 degrees, 225, 135, and 45 degrees. So we actually end up with 4 solutions. And all of these have a secant value, either plus or minus square root of 2, and also a cosine value of plus or minus square root of 2 divided by 2. So we end up with actually 6 solutions from 0 to 360. So in the next couple of examples, we're going to be looking at using identities and then factoring to solve these equations. In this example, we are asked to find all solutions of this equation. So we're asked to find all possible angle solutions for theta. And since we're working with theta, we're going to look for answers in degrees. Now this one's a little bit different because we see that we have sine theta and we have cosecant theta, so we have 2 different trig functions. And if we were to think about this in terms of the algebra, if we think about sine as being a variable, let's call that x, and cosecant being a variable, let's call that y. If we were asked to solve this in algebra, we would have a hard time doing that because we have 2 variables and we only have 1 equation. Solving equations requires that if I have 2 variables, then I have 2 equations. If I have only 1 equation, then I need to have only 1 variable. So let's think about this. If I go back to the trig equation here, is there a relationship that I can manipulate between sine and cosecant? And the answer is yes. We can actually use the reciprocal identity. So we can write this as sine 2 times sine theta minus 1 equals 1 over sine theta. And if we think back to the algebra now, that looks like this now. 2x minus 1 equals 1 over x. So we have 1 over sine, and we said sine was like x. So now we have this. Well, how would we have solved this in algebra? Well, we want to multiply everything through by x so that we don't have a variable in our denominator anymore. We're going to do the same thing here. We're going to multiply by the LCD. In other words, we're going to multiply everything through on both sides of this equation by sine theta. That way sine theta is not in the denominator anymore. So we're going to multiply through by sine theta. So we end up with 2 times sine squared theta minus sine theta equals, and then if we think about this as a fraction, we multiply across, we end up getting 1 because those sine thetas will cancel out. So now we have something that looks like 2x squared minus x equals 1. And if I was working in algebra and also working in the trig, I was going to get everything over to one side and then we're going to factor. So let's subtract 1 from both sides. So you have 2 sine squared theta minus sine theta minus 1 equals 0. So we get everything over to one side and then factor. So we have 2 sine theta and then sine theta. So first times the first has to give us the first. And we look at the last, we have minus 1. The only options here are 1 and 1, and we need a plus and we need a minus. So I'm going to put the minus here and the plus here. And let's check it, make sure that if I FOIL it out, I get back the correct middle term. And we do. Right. So let's keep going. Now that it's factored, we're going to set each one of these factors equal to 0. Now we have 2 different linear equations that we want to solve. We're going to subtract 1 from both sides here. And then divide both sides by 2. Get sine theta is equal to 1/2. And the other one's very easy to solve. All we have to do is add 1 to both sides. And now we have sine theta is equal to positive 1. So looking at the first problem here, sine theta is equal to 1/2. What angles have a sine value of positive 1/2? So we're looking in quadrants 1 and in quadrants 2. And we're looking for a y value on the unit circle of 1/2. So that would be right here and right here. That's our 30-degree reference angle family. So going into both quadrants, 30 degrees. And let's remind ourselves we're working in degrees. So we're looking at theta equals 30 degrees. And also, theta is equal to 150 degrees. So those are the 2 angles, and from quadrants 1 and quadrants 2 that have a sine value of positive 1/2. Now we're also asked to find an angle that has a sine value of positive 1. So where would that be? Well, we're looking for where we have a y value, then a positive 1 on the unit circle, and there's only one of those, only one place on my unit circle where we have a y value positive 1, and that's at 90 degrees. So we end up with 3 solutions for those two equations there, those 2 linear equations. And we're asked to find all possible solutions. Now these are not equally spaced, these 3 solutions are not equally spaced around the unit circle. 30 and 150 are not halfway around the circle from each other. So in order to give all possible solutions, we're just going to take each one of these angles and add 360 in. So we're going to add multiples of 360. So here's how we would give all possible solutions. The 3 angles on the unit circle plus multiples of pi to each one to find all possible coterminal solutions to those angles as well. So in example 9, we are asked to find all solutions of this equation. 5 plus 5 times tangent squared theta equals 6 secant theta. And here we once again have 2 different trig functions. So if we were solving this in algebra, it would look something like this. 5 plus 5 times, let's say, x squared equals 6 times y. Once again, we run into a problem because we have 2 different variables and we only have one equation. One thing that we could try first is to bring everything over to one side and see if anything will factor. Well, nothing is going to be able to factor out of all 3 of those terms, so that method won't work. The next thing we want to try, if factoring doesn't work, is to try using an identity to get everything to be in the same variable. So what is a relationship between, let's say, tangent and secant? And we want to keep in mind that we do have a tangent squared. And that should sound like a Pythagorean identity. So tangent squared theta plus 1 is equal to secant squared theta, where this is our Pythagorean identity. We want to replace just tangent squared theta with something that is equivalent to it. So let's subtract 1 from both sides. We get that tangent squared theta equals secant squared theta minus 1. So we can replace tangent squared theta with secant squared theta minus 1. So let's do that. Okay. So we're going to bring down the 5 plus 5, and we're replacing tangent squared theta with its equivalent, secant squared theta minus 1. And we're going to bring down everything else. Now we only have one trig function within our equation, and that's what we want. So we're going to get rid of the parentheses by doing a distribution. So now we have 5 plus 5 times secant theta minus 5 equals 6 secant theta. And we notice that we have a 5 and then a minus 5. So these are going to cancel each other out. So now we have 5 secant squared theta is equal to 6 secant theta. Our goal is to get secant theta by itself on one side. So what we're going to do is we're going to subtract. We're going to get 0 by itself on one side, everything else on the other, and then we're going to try to factor. So we're going to bring everything to one side. So we have 5 secant squared theta minus 6 secant squared, or secant theta. There we go. So once everything is in terms of secant only, we're going to try to factor. We're going to bring everything over to one side and then try to factor. Well, what is common between those two terms? They both have secant theta. So let's factor out secant theta. So that's secant theta times 5 secant theta minus 6 equals 0. Now that it's factored, we can set each one of these factors equal to 0. And then we'll have 2 equations in linear form that we can solve for secant. Okay, well, the first one is secant theta equals 0. And keep in mind that we may not be familiar with the secant values, but we are familiar with the cosine values, so let's go and let's change this to be the reciprocal function. So the same angle that would have a secant value of 0 would have that same angle would have a cosine value of the reciprocal of that. Well, the reciprocal of 0, if I think about this as over 1, and I flip that fraction, I get 1 over 0. There's no angle that we know about that has a cosine value that is undefined. If we think back to the domain and ranges for secant, what are the allowed output values? Or in other words, the range for secant. Well, secant, those output values go from negative infinity to minus 1, and then from 1 to positive infinity. Let me write that straight. So secant actually never achieves a value of 0. And cosine actually never has an output value that's undefined. So there's no solution to this part of our equation. Okay, so this will not yield a solution. But we might still be able to find a solution from this part. So let's solve for secant. Let's add 6 to both sides. We have 5 secant theta equals 6. Divide both sides by 5. Secant theta equals 6 over 5. Not an angle, not a value for secant that I'm familiar with. So let's change it to be cosine and see if that looks more familiar. So the same angle that has a secant value of 6 over 5, that same angle would have a cosine value of 5 over 6. Well, once again, not familiar with that cosine value. So let's put this into our calculator. Cosine inverse of 5/6 equals what angle? And once again, we want to keep in mind that we are looking in 2 quadrants for this solution. We are looking in quadrants where cosine is positive, since we're looking for a positive cosine value, which would be quadrants 1 and quadrants 4. So when we put this into our calculator, we're looking for angles in degrees. Let's go ahead and round to the nearest tenth here. And when I put this into my calculator, I get 33.6 degrees. So this will be the reference angle that we end up using. So the distance from the x-axis to the point in quadrant 1, that is a 33.6 degree reference angle. So one of our solutions is 33.6. That's in the allowed interval from 0 to 360 there. And then I'm going to find the same reference angle in quadrant 4, and what we want to know is if this distance is 33.6, what we're actually looking for is if I start at the x-axis and go all the way around and I stop at this point right here, what angle is that? So what quadrant 4 angle starts here and goes all the way around and stops here where we have a reference angle of 33.6? Well, in order to find that, we have almost a complete rotation, except we stop 33.6 degrees short of going all the way around the circle. So we stop right here. How would I determine what that angle is? Well, we would have to take 360 degrees and subtract from that 33.6 degree reference angle. So what we actually get then is 326 degrees. 0.4, so we'll round to the nearest tenth. So remember that we want to find all possible angles on the unit circle, and we use reference angles to determine how far into each quadrant that we're going to go from the x-axis. So we're asked to find all possible coterminal solutions to this as well. So for each of these, since they're not equally spaced and are not halfway around the circle from each other, we are going to just add 360 in plus 360 degrees times n. So these will be all possible solutions to this equation. So the two angles that we found on the unit circle plus all possible coterminal solutions to those two angles as well. Alright, we're at, for example 10, we're asked to solve the equation 9 times sine squared theta minus 6 sine theta equals 1. And we're asked to solve over the interval from 0 to 360 degrees. So if we think about this in terms of algebra again, we would have 9x squared minus 6x equals 1. So the first thing that I would try to do is bring everything over to one side and try to factor. So let's try that. Let's subtract 1 from both sides. And if we were to try to factor this, we would try either 9 sine theta, or we could try 3 and 3 sine theta. So we're going to run into a little bit of a situation here because this, no matter what we try, is not going to factor. So you can try all kinds of things, but it's actually not going to factor. Now if something doesn't factor when we are in algebra, what do we do? Well, we would use the quadratic formula. So once I get everything over to one side, 0 on the other, and I try to factor that, if it doesn't factor, we would use the quadratic formula. So let's remind ourselves of what that quadratic formula is. That would be x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So we were in algebra and we tried to bring everything over to one side, 0 on the other, and we tried to factor that, and we couldn't factor it, then we would say x equals all of that. Now in this analogy, x represents sine theta. So if we were to actually use the quadratic formula here, the a is of course whatever's in front of x squared, or whatever's in front of sine squared, that would be 9. The b would be whatever's in front of the linear term, which would be minus 6, and the c always represents the constant, which would be minus 1. So instead of writing x equals or theta equals, excuse me, we want to be careful. Over here in our analogy, x represents sine theta. So if we go back and replace that, what we're actually solving for is sine theta equals, what we're actually getting is a sine value. And we have to determine the angle that would have this sine value. So let's use our quadratic formula here. That would be minus b, so minus a minus 6, plus or minus the square root of b squared, so that would be minus 6 squared, minus 4 times a times c all over 2 times a. So you do need to know the quadratic formula just like you had to know it in college algebra. Now we're going to simplify this, but we don't have to worry about simplifying it too much because we're just going to put this into our calculator as it is obviously an unknown sine value. So let's just simplify minus 6 is positive 6 plus or minus the square root. Negative 6 squared would be 36, and that would be plus 36 all over 18. Let's simplify just a little bit more. We have sine theta equals 6 plus or minus the square root. 36 plus 36 is 72 all over 18. Now we're going to stop simplifying there because we're going to let our calculator do most of the work for us here. Now keep in mind that we do have two sine values because we're looking for plus and for minus. So let's separate these. Let's think about this as sine theta equals 6 plus square root of 2 over 18. And then sine theta equals 6 minus the square root of 72 all over 18. So that plus minus separates into two separate solutions. So what we're looking here, since this is an unfamiliar sign value, let's put this into our inverse function. Now, what I recommend doing in your calculator is go ahead and type in this value by itself first. So in your calculator, before you go and use the inverse function, type this into your calculator first. And then we're going to work with that approximation. And you're going to leave that in your calculator and let your calculator store all of that information for you, so we don't have to retype it. But when I put this into my calculator, I get something that looks like this. And what we're going to do is we're going to use the answer button on the calculator to actually, we're going to go second sign inverse, and we're going to say second answer, and let the calculator use this entire value that it had stored already in our calculator. And then we're going to hit sign inverse, we're going to do all of that, put that in, and then the angle that we get for this, and make sure your calculator is in degree mode because we're working in degrees for this one, is we're going to round to the nearest, let's round to the nearest tenth again. I get 53.6 degrees there. Now that is a positive sign value that we got from using that quadratic formula. And in our unit circle, we know that sign is positive in two locations. Not only 53.6 in quadrant 1, but also we want to use that as our reference angle. So the distance from the x-axis to this point, 53.6, we're going to use that same distance and we're going to go into quadrant 2 that exact same amount. And we want to know, if we started here and went all the way to this point, what would this angle be? So we're going to have to do 180 degrees minus that reference angle, 53.6 degrees. So to find that quadrant 2 angle there, we're going to subtract from 180. So 180 minus that reference angle, we get 126.4 degrees. So here's two solutions, and we're going to find two more solutions with the second value here for sine. So once again, my recommendation is to put this sine value into your calculator first and let your calculator already have that value stored. And then once you have that value in your calculator, then you're going to hit the sign inverse button, and you're going to hit second answer and let your calculator put everything in that it has stored in the calculator. So that I get minus 0.1380711187. So let your calculator use as much as it has already stored so we get the most accurate angle possible. And remember that your calculator is going to give you a negative value, so that's to be expected. The inverse function, if you put a negative sign value in, it's going to give you a negative angle out for that sine inverse function. So it's going to give us a negative angle from quadrant 4. So we're going to get negative 7 point, and let's round to the nearest tenth, negative 7.9 degrees. Now keep in mind that we don't want a negative angle. We're asked to find solutions from 0 to 360. So we don't want a negative solution. So let's look at on our unit circle here. And if our calculator gives us negative 7.9 degrees and we want a positive coterminal angle to that, so we want that angle in quadrant 4, but we want to think of it as a positive angle, well, we're going to add 360 degrees to that angle. And so what we actually get is a positive coterminal angle, 352 point, I get 0.1 degrees. So there's one of our solutions in quadrant 4. And we also want the other quadrant angle where sine is negative. So sine is negative in quadrant 4 and also in quadrant 3. So if I go into quadrant 3 using that same distance from the x-axis to the angle, that same reference angle, 7.9, 7.9 degrees is my reference angle. What angle would that be? So this time we're working in quadrant 3. So I want to know what quadrant 3 angle has a reference angle of 7.9 degrees. So in this case, we want a complete full rotation, 180 degrees, and then we want to go a little bit more into quadrant 3, 7.9 degrees. So we're going to add 180 to 7.9. And that quadrant 3 angle turns out to be 187.9 degrees. So we get two solutions here from quadrants 4 and quadrant 3. 352.1 degrees and then also 187.9 degrees. So we have a total of 4 solutions, 2 that came from quadrant 1 and 2, and then we have 2 more that come from quadrant 3 and quadrant 4. So in this last example for solving trig equations, we want to look at a different method that we can use, and that is squaring both sides of the equation so that we can use a Pythagorean identity. So in this case, we have tangent x plus square root of 3 equals secant x. And we're asked to solve over the interval from 0 to 2 pi, so we're working in radians. Now, if we think about the algebra again, and I always encourage you to go back to the algebra and think about the problem, and we think about tangent x as being x, and secant x as being like y, we have a little bit of a problem here once again because we have 2 variables, but we only have 1 equation. And it would be great if we could only work in 1 variable. If we bring everything over to one side and try to factor, nothing's going to factor. So our option here then is to use identities. However, the problem is when we look at our equation, I don't have tangent squared, and I'm looking for a relationship between tangent and secant, and the only relationship that we might be able to think of would be that Pythagorean identity. But the Pythagorean identity is only going to work if we have tangent squared or secant squared. So in order to make this happen, we would want to square both sides of the equation. Remember that we're allowed to do this because whatever I do to one side, as long as I do the same thing to the other side, we will have an equivalent solution for x. Now be careful, when you square both sides, it's tangent x plus square root of 3 times itself. So tangent x plus the square root of 3. So be really careful when you square that 2-term side of the equation. Equals, now the other side, when we square secant x, we just get that 1 term, secant squared x. So over here we need to FOIL though. Tangent x times tangent x, I get tangent squared x. Outer times the outer, I get plus square root of 3 tangent x. Inner times the inner, plus square root of 3 times tangent x. And last times the last, square root of 3 times the square root of 3. That would be the square root of 9. And then let's simplify as much as we can. Here we have tangent squared x, no like terms there. Square root of 3 tangent x plus square root of 3 tangent x, that would be plus 2 square root of 3 times tangent x. And then the square root of 9, of course, is 3. Now, when we look at our equation, we see that we still have a situation that we have 2 different trig functions and only 1 equation, and we only want to have 1 type of trig function. Now we have the tangent squared x and we have the secant squared x. Which trig function should I want throughout my equation? Well, since we have this tangent x that's not squared, it would be really nice if we had the entire equation in terms of tangent. Because this tangent x is not being squared, it's not going to go away. So if I had everything in terms of tangent, then my equation would be only in one trig function. So let's replace secant x with an equivalent expression using our Pythagorean identity for tangent and secant. So that would be tangent squared x plus 1 is equal to secant squared x. So let's replace secant squared x with tangent squared x plus 1. Okay, so now this is the equation that we want to solve, and we have everything only in terms of tangent, which is what we were looking for. Okay, so we're going to bring everything over to one side, and then we're going to factor. So we're going to subtract tangent squared x and minus 1 from both sides. Everything's gone from this side, now we have equals 0. And over here, well, the tangent squared x's cancel each other out, so we're left with 2 square root of 3 tangent x, and then 3 minus 1 gives us positive 2. So it simplifies to be something really nice. And then, of course, we want to solve for tangent x, so we'll subtract 2 from both sides. 2 square root of 3 tangent x. So we don't need to factor anymore because we lost that square term. So we're just going to solve this linear equation, or linear form of the equation. Divide both sides by 2 square root of 3. So you get tangent x is equal to, and we're going to cancel our common factors here. So we get 2 divided by 2, that gives negative 1 divided by the square root of 3. And now we're looking for the solutions here. Our tangent is negative, so we're looking in quadrants 4 and quadrant 2. And remember that tangent is y over x. And before we go and rationalize it, let's think about what 2 points would simplify to be 1 divided by the square root of 3. And on the unit circle, we either have 1/2 or square root of 3 divided by 2. So let's think about this as being like a negative 1/2 divided by square root of 3 over 2. So what angle family are we talking about? Well, we need a y value of 1/2 and an x value of square root of 3 over 2. So it looks like our pi over 6 family, or our 30-degree reference angle family. And we were originally working in radians, so let's use the radian values. So that would be 5 pi over 6 or 11 pi over 6. Now, one of the things that we have to be careful about is that we want to make sure that we check both solutions in the original equation. So when we square both sides, we have to be careful that we check our solutions. Sometimes squaring both sides gives us solutions that don't work in the original equations. So we're going to go back to the original equation and we're going to check both of these solutions. Alright, so here's our original equation from the top of the page. We have tangent x plus square root of 3 equals secant x, and this is what we were originally asked to solve. So we want to check these two solutions, 5 pi over 6 and 11 pi over 6 in the original equation. So let's go for 5 pi over 6 first. Let's check that. So that's tangent of 5 pi over 6 plus the square root of 3 equals the secant value of 5 pi over 6. So if we go back and we look at our unit circle, so let's shrink this down a little bit. 5 pi over 6, the tangent value of that was negative 1 over the square root of 3, or square root of 3 over 3, and that was a negative value. So let's go ahead and rationalize that. instead of writing it as 1 over the square root of 3, let's write it as negative square root of 3 over 3 plus the square root of 3 equals the secant value of 5 pi over 6. If we go up to the top, the secant value, of course, would be the reciprocal of the cosine value. So that would be negative 2 divided by the square root of 3. So does this add up to give us what we want? And let's see. So we would need to give them both the same denominator here. So when I add these two sides together, that would be LCD of 3. So if I multiply the bottom by 3, I got to multiply the top by 3 as well. And when we add these two together, we get 2 square root of 3 over 3. And notice that that is a positive value. On this side, if I was to rationalize to make both sides look equivalent, we would get still negative 2 square root of 3 over 3. And these are obviously not equal to each other. They are different by a sign. So that's what happens when we square both sides. It makes both sides appear to be positive after we square them, and then we solve the equation. We want to make sure that we check in the original before we do any squaring at all, when both sides could have potentially turned out to have opposite signs. So 5 pi over 6 is actually not a true solution, so we're not going to include that on our answer line. Let's check the other one, the other solution, 11 pi over 6. So tangent of 11 pi over 6 plus the square root of 3 equals secant of 11 pi over 6. So 11 pi over 6 has a tangent value of negative square root of 3 over 3 plus square root of 3 equals, now the secant value here in quadrant 4 is positive. So that is the reciprocal of the cosine value, so that would be positive 2 divided by the square root of 3. And here, if we add the two fractions on the left-hand side, think about that as over 1, and give them both the same LCD, that would be 3. So on the left-hand side, we get positive 2 divided by the square root of 3 over 3. And on the right-hand side, if we were to come in and rationalize, we would get also positive 2 square root of 3 over 3. So this works out. They're both positive values. They turn out to be exactly the same on both sides of our equation. So we're going to keep 11 pi over 6 as our only true solution for this equation. So be careful, if you square both sides of an equation, make sure that you check your answers in the original to make sure that both sides actually do balance out using that specific angle.